this sort of thing had a similar thing with these sort of sensors. Long more that it got close to one sensor and it triggered off the sensor. The sensor thought it was, you know, these sort of northern lights going on, if you like, for it. So what we might have to do is to smooth out or filter some of that noise using some data smoothing techniques. Just as an example, like if I had a bit of data going through, I might say, well, look, I've got my little distance sensor, say in the top of this pen, and I'm measuring from here to that top corner. Now, my you know, I've got a bit of palsy or whatever, my arm's sort of bouncing about all over. And if I'm measuring the distance, this might be distance over time, I start to measure the distance. And that might be the sort of line that's measuring the distance up to that sort of corner. But hopefully you know that because of that, I can perhaps sort of say, well, really that's a straight line going through it. And I'm just going to smooth out that data to what's sort of in there. Or it might be that the data's sort of bouncing around all over the place, going up and down. And you might sort of apply some smoothing onto that and say, well, actually, that's like almost like a sine wave going through, and you can sort of approximate that. Now, there's various techniques you can get for smoothing out this data that's coming in from the outside world. Or, in another sort of case, we're running out of sort of space on this, your data might be sort of happily going along, and I'll do it over here. All of a sudden it spikes up and carries on. Do you want to ignore that spike for it? Or is it something, yeah, it may be that you want to ignore it. It might just be, that's the motorbike going past your sensor on your car, and you want to tell your car alarm not to go off. It may be that that is somebody trying to break in. So sometimes it's significant, sometimes it's not, but you probably at some point want to apply some sort of smoothing technique onto your data and get some sort of average of it. So you can say, well, let's take all these little values that you've read, all these X points for the data values, and I'll just average them out. And hopefully get a straight line onto it. Now there's various statistical techniques that'll do this sort of thing for you to get it, where you can just say, well, I'll take a value X, that's the sort of values going along the straight line, at position -1, +1. You take a series of values and say, well, let's just average those out. And then let's move along and let's average 10 values out there. Let's average 10 values out here. And you get what's called a moving average as you're going through. And what it tends to do is to smooth out that data. Now that might be done inside the sensor itself, but more realistically, it'll be up to you to do. Now it may not form part, in our case, of say the assignment that we're doing, but if you're dealing with data flooding in, you might want to do this sort of smoothing out, a bit of auto-regression, as they call it, to do that sort of analysis. And you might want to start looking at, as I say, sort of moving averages, where you sample out, in this case here, 7 values, take 7 values, take a seventh of that, and say, okay, well that's my average value that I want out of it. And then I'll take the next 7 values and the next 7, or however many you want that sample size to sort of be. Now I realise that sort of started to get a bit mathsy, really, for it. But it's just something that you need to be aware of, noise coming in, of the accuracy of these sorts of things, and can it repeat it, and what's the resolution. Now in terms of putting a node together, a node, might be a very specific one, like this heater controller. That's for controlling radiators. You don't use that for, say, opening your windows with. You don't use it, somewhere in your car. It's specifically just for that. If you want a generic idea, what you can also buy are sort of nodes that have got everything built into them. This is one particular one, with just sort of giving you an idea of the size there for it. And the idea is that we're trying to turn objects into things. A thing that becomes smart when it's got some sort of communication with the outside world, some sort of sensor to detect, a bit of control in there, a bit of way of communicating, and some sort of power supply. Now again, this thing fulfills those. It's got the sensor and an actuator in it. It detects temperature and it can turn a little motor. It's got a processor inside it. It can send its message out to that hub. And it's got a power supply, in this case a battery. For it. Similar thing with the, eventually made it back down, the flicked one. Not necessarily as sort of big a thing as that. This has got a sensor, there's just a little button inside. It can detect 3 types of presses to sort of work with. It's got a power supply in it. It's got a little tiny, like a watch battery inside. It's got a communication unit that's Bluetooth to get to that, whereas this is sort of more like a radio wave approach. And it's got a tiny processor built into it. So both of these are nodes. Really. They can both gather information from their environment and send it out. Sometimes it may sort of actuate on it. Typically it's powered by a battery, and that limits the source of energy, because you're normally placing these in places where there's not necessarily a power supply. You don't want to be plugging in, say, your radiator. You don't want really, water and electricity don't tend to mix too well. But also you might have the sensors up high somewhere. So it might be on the ceiling, like you have your smoke detectors. You don't normally run, say, a power supply to that. They're generally small, low in cost. That limits their computing capability, and we'll look at the problems of that. And they don't normally perform complicated tasks. This has just got to send a temperature and turn a motor. It's not Windows 10 in here. This doesn't have Windows 10 loaded on it. All it does is pick up a button press and send it on. So it doesn't need to be a powerful processor on it. And actually it's this power consumption that's the main design issue for our nodes. Because that's the sort of generic layout of a node to it, with some way of communicating to the sort of outside world, and we'll look at communications in a separate lecture for it. Microcontroller in there, not the latest Intel, whatever it is, such a gigahertz processor, but it's only controlling something small. So you can use really cheap processors in there. A few sensors and actuators connected to it, one or the other, or both. Typically battery powered because they're limited supply. And generally some sort of flash memory, so it can remember the last state. So if there is a power cut, or it's starting up again, it can remember the last sort of state of it. But when we think on this as well, though, it's got to, it's not only got a processor in here and memory, it's actually got an operating system in here. There's got to be a full-blown, not full-blown operating, but a operating system's got to be on here. Now that won't be, as I say, Windows 10 or Linux or whatever's sort of running in your Mac or something like that. It's got to be something really low powered. It won't be Windows 95 or Windows 3.1. Well, for one thing, it's not operating a screen, so it doesn't need all those screen handling capabilities. It just needs to do what the basic thing is. And next week we'll have a look at the networking and operating system part of it. Now, just to finish off today, just give you an example of a sample standalone node. This is one from this Advantix company. That web address there, I just made sure it was still live this morning. This particular node sells there for about €95. Now, that's just to show that it's still available and its facilities are still there, but I'll go back to the slide to go over its capabilities. These nodes just give you an idea of how cheap they can be, or how, when I say cheap in terms of their facilities. This particular node has got 8K of RAM. Now, how much memory is in your phone? You're talking about gigabytes. You're talking about millions of bytes. This is 8,000 bytes. It's not even a megabyte. It's not even a megabyte, and a gigabyte is 1,000 megabytes. So tiny, tiny memory. 116K EEPROM in there. But it's got built into it some light sensors, temperature sensors, etc. The processor there, a 16-bit RISC architecture, how much memory it's got, what interfaces it's got to the outside world, so how can it communicate? It has got a USB built in. What sensors it's got ready connected to it. It's got a couple of light sensors, and again the ranges of that, how much light can it detect, what ranges of it. Temperature and humidity, what ranges of temperature can it detect. So that's really the specification of a particular programmable node. Now that node can then be used out in the field. It's got ready built into it a couple of sensors to it, and it can communicate. And we'll look at how you might get communication over sort of long distance.